Okay, I really hope this records in the right format because a video that I just recorded for physics wasn't, and so I had to redo it, and so here we go. All right, so here's where we left off talking yesterday. We were getting fairly philosophical about entropy and the fate of the universe. And so we're going to just continue kind of that theme and get more into the mathematical side of this and kind of like heat flow and all this good stuff. So let's say that we're going to take a piece of ice and we're going to put it out on the table, okay? And we're going to look at this from a couple of different perspectives, heat flow and entropy. So if you look at the system and the surroundings, so we're going to call the ice the system, and we're going to call the air around it the surroundings. So the first thing we have to look at is the direction of heat flow. So on your heat flow, obviously if ice is going to melt, energy has to flow into the system. So this is this idea also of energy goes into a system to break bonds, okay? So this is going to be important. Energy is flowing into the system. So that means that you're going to have, in this case, a positive delta H, because it's an endothermic reaction, basically. Energy is flowing into that ice because you have to break bonds, okay? So that's the first thing that's going to happen. Now, the surroundings out here, that's what's going to lose the heat. So if you look at what's going to happen, since energy is flowing into the ice and the amount of energy has to stay constant. So we're increasing the ice energy, okay? So the ice energy is increasing, which is your system, but we're decreasing the energy of the surroundings. So the air is cooling down. So this is why, as you go into summer and you're going to have, oh, I want a glass of iced tea. From a thermodynamic standpoint, that ice is acting as a heat sink. It's absorbing energy from the tea, and that energy is going in to break the bonds that hold the ice together. So from the iced tea perspective, you're losing energy. From the ice cube itself perspective, you're gaining that energy, because that energy is going to break bonds because that ice is going to melt. So that energy is flowing from the tea into the ice. So now, from an entropy standpoint, okay, from an entropy standpoint, because the air is cooling down, or the tea is cooling down, that's not going to have as much entropy, okay, because of the fact that it's losing that energy. It's like, you know, you've got second graders out playing around on the playground and it's 70 degrees. Well, all of a sudden a cold front comes through and that temperature drops to like 40 degrees and the wind is blowing out of the north, okay? Those kids aren't going to have as much disorder because it's colder. So the surroundings, okay, because of the fact that it's cooling down, is going to lose entropy. But, because we're changing from a solid into a liquid, the entropy of the ice is going to increase, okay? Because of the fact that you're going from the solid structure, very ordered, into a situation where you're going to have more disorder as a liquid. So I've got a positive delta H because it's endothermic. I'm going to have a positive delta S because I'm increasing the entropy, because of the fact that I am making this go from an ordered, structured ice cube into a liquid. So what this means is that I've got a positive delta H and a positive delta S. Now, Mother Nature likes this situation from an entropy standpoint because we're making the room more disordered. She doesn't like it from an enthalpy standpoint because of the fact that it's an endothermic reaction. So Mother Nature likes exothermic reactions where you have a negative delta H with a positive delta S. So Mother Nature is batting 500 in this situation. She's got the positive delta S going her way because you're increasing the disorder. You got a positive delta H, not so much, because that's an endothermic reaction, okay? So, when you look at this, so the delta S for the system, that's going to be a positive delta S. For the surroundings, that's going to be a negative delta S because of the fact that the surroundings are cooling down and it's not going to have as much disorder. Cool with this. Now, let me kind of get rid of some of this. So here's kind of this big idea. Okay? Kind of highlight all of this. So, when you look at this, so this should make sense. A reaction that is exothermic for the system will increase the entropy for the surrounding, because if it's exothermic, remember, it's releasing energy. You're giving Timmy Skittles, okay? And we'll have a positive delta S for the surroundings because of the fact that it's giving that energy. Now, because it's exothermic, we also have a negative delta H. So, if it's an endothermic reaction, okay, then for the surroundings, that's going to cool down. You have a negative delta S for the surroundings and a positive delta H for the system because of the fact that it's gaining that energy. Okay, so in terms of equations, let's talk about this one. We'll change the color a little bit. We'll go back to the traditional highlighting of yellow. So delta S for the surroundings is equal to negative delta H divided by T. Now, let's talk about the units. So when you look at this from a units value, so this is typically going to be in joules or kilojoules per mole. And then this temperature has to be in Kelvin, because that gets us out of using Celsius where you could have 0, which would be undefined, or you could have negative numbers, which would also be jacked up. So the units for delta S for the surroundings are typically given as joules per mole Kelvin, mainly because of the fact that the values are so small. Now, so at this point, you should have enough understanding to realize, oh, we can measure delta H. Now, notice that there's a negative sign out here. So if delta H is positive, then you put that negative sign, because this is going to be for the system, then that's going to switch the sign for the surroundings. You're going to divide by Kelvin, which is always going to be a positive value. So if you have a positive delta H, which means it's an endothermic reaction, you put that negative sign in front of it, that switches the sign for the surroundings. So this is for the system, this is the temperature. So if you think back to that copper sulfate lab, or anything, you can measure what happens to the surroundings. So we can calculate delta H. That's something that we can observe. We can measure the temperature. Oh, okay, cool. Then from that, we can figure out what's going to happen with the surroundings. Okay? So, again, we don't have an entropy measuring device, but we can measure enthalpy, we can measure temperature, and then from that, we can get the delta change in the entropy. So, if it's an endothermic reaction, delta S for the surroundings is negative, and delta H is positive. Exothermic, delta S for the surroundings is positive, delta H is negative. Okay? Because it's like a negative of a negative. That makes sense. All right. So there's two big laws of thermodynamics. First law is that basically energy is conserved. Right? So the amount of energy, and Einstein tied mass into this by E equals mc squared. M is mass, C is the speed of light. Here's your energy. No, I'm not going to expect you to do any calculations with this. But this is what drives the sun, because hydrogen is slamming into helium, and you have 4 hydrogens that are making helium. There's a slight change in mass. Multiply that by the speed of light squared. You get energy. Hey, our local star is producing a tremendous amount of energy, and that's a good thing. So, basically, all this says is that we're going to keep the amount of energy in the universe a constant. You can change its form, but that's all. Okay, so now, The second one, second law of thermodynamics, speaking of entropy, let's make it thin. Okay? So, now notice there is this word always. Okay? Notice that there is this word always. In a spontaneous reaction, we increase the entropy of the universe. And when I mean the universe, I mean the universe. Okay? I'm talking big picture universe kind of thing. So, to calculate delta S of the universe, this is delta S of the system plus delta S of the surroundings. So basically, let's say for example that you want a positive delta S. So if the system's increase in entropy is say positive 8, okay? And the corresponding decrease in this is like negative 6. Oh, hey, that's going to get you positive delta S from the universe. It's going to spontaneously happen. Now, what is going to happen in terms of like this room is that this room is not going to spontaneously clean itself. And I know that because delta S of the universe is not going to increase, and that's going to be a positive value. What's going to happen in terms of this room cleaning itself? It's not going to. So I know that spontaneously cleaning rooms isn't going to happen because you don't increase the entropy of the universe. That's why things don't clean themselves. Okay, so if you have a positive delta S, the reaction is spontaneous. If you have negative delta S, it's not spontaneous, but it could be spontaneous in the reverse direction. So hydrogen and oxygen combine to produce water. Oh, that's a spontaneous reaction. Water is not going to decompose into hydrogen and oxygen. But if you reverse it, then it could be. So that's all that's saying here. Now, if delta S is, for this universe, is 0, that just means that the system is in equilibrium. We're not increasing the entropy, we're not decreasing the system, or the entropy. The system is just at equilibrium. Okay, so here's kind of the big thing. So, no process that produces order, okay, a lower entropy, in a system can proceed without producing an equal or greater amount of disorder in its surroundings. So let me give you an example. So I walk in, and rare that this happens, I get the urge to clean. Rare that that happens. So I'm going to go through and I'm going to tidy up my papers, okay? I'm going to do this, okay? Grab these, okay? Kind of organize. Here's my physics book, okay? Put that in here. We'll put this on here so we don't lose it. Kind of tidy things up. Okay, so I have decreased the entropy of this area. But in doing that, I've increased the entropy of the area around me. I was moving, okay? That disturbed the area. My body was giving off thermal energy because that's all we are, is just basically, you know, little engines, okay? And we're furnaces and we're giving off all this energy. So my body is radiating this heat, that's increasing the entropy. So basically, I know that this is not a spontaneous reaction. So my increase in the entropy of the room was greater than the decrease in the entropy of cleaning. That's why this cleaning of the room is a non-spontaneous reaction. Okay, so that's kind of the big philosophical side of it, all right? So let's talk kind of the mother of all equations. So if you look on your equation sheet, so on the bottom here of this equation sheet, you have, delta G equals delta H minus T delta S. So this right here, delta G equals delta H minus T delta S. So this is kind of the mother of all thermodynamic equations. So let me explain the subtleties of what's going to happen here. So on this delta H, this is your change in enthalpy. So this could be a positive or a negative value. Delta S, this is going to be what's going to happen with the system. That could be positive or negative. And this is going to be a temperature that's in Kelvin. So this is why I said you have to pay attention to the units. So your delta H is typically in kilojoules per mole. Your delta S is typically given in joules per mole Kelvin. And then that temperature has to be in Kelvin. So, especially on that quiz that I just gave back to you, on that thermodynamic quiz, some of you are not paying attention to the units. So this is a situation where you cannot just blissfully write down numbers. So, when you look at this, if you're going to keep this in kilojoules, then you have to change your delta S into kilojoules. If you're going to change this into joules, hey, that's cool. Then you can use your delta S as joules. I don't care. You just have to pick one, okay? I don't care. Now, let's talk about what Mother Nature likes. So you could have 4 different options. You could have a negative delta H and a positive delta S. You could have a negative delta H and a negative delta S. You could have a positive delta H and a positive delta S. And you could have a positive delta H and a negative delta S. Okay? Now, if there's anything that you begin to memorize and actually spend some time thinking through, it's these 4 possible combinations. Okay? Now, if you look at this equation, delta G equals delta H minus T delta S. So if you want a spontaneous reaction, you know you have to have a negative delta G. Okay? Old school. Gibbs free energy, negative delta G, you get a spontaneous reaction. Now, what we're going to look at is the first combination. We're going to have negative delta H minus some temperature times delta S. Now, look what happens here. You got a negative value here, okay? This is going to be a negative value. Minus the temperature, because we're in Kelvin, that can't be a negative value. And then you've got a delta S, which is your increase in, because you have a positive delta S, you have an increase in entropy. Mother Nature loves this combination, okay? Because what's happening is that you have both terms driving this thing towards spontaneity. You have a negative delta H, it's an exothermic reaction. Oh, Mother Nature likes that. Oh, she likes a good fire, okay? You have an increase in entropy. Mother Nature likes a mess. So both of these things are driving it towards spontaneity. If you're a math nerd, okay, you're going to have a negative number here, minus T, times a positive delta S. So you can have a negative minus a positive number, which is also going to generate a negative delta G. So if you wanted to look at this mathematically, you could go, oh, okay, well, I'm just going to make up a number. Let's say that that's negative 5, and let's say that the temperature is 2. It's really low, okay? It's 2 degrees Kelvin, but it's going to work. And let's say your delta S is 4. So I'm going to have negative 5 minus 8, which is going to give me negative 13. So as the temperature goes up, the only thing that's going to happen is that this is going to become a bigger and bigger and bigger negative delta G value. So here's the point. When you have a negative delta H and a positive delta S, this combination here is always, always, always spontaneous. Okay, there's no exceptions to this rule. When you're so you see a reaction and it's giving off energy, and you're increasing the entropy, that reaction is always going to happen. It's always going to be spontaneous. Now, I want to jump back down. I'm going to go down to this one. A positive delta H and a negative delta S. Now, if you look at what's going to happen here, I got delta G. In this case, it's going to equal 5 minus 2 times and negative 4. Okay? Now, here mathematically, here's what's happening. I got 5. I've got a positive delta H, so it's an endothermic reaction. Mother Nature's going, oh, Skippy, this is not good. Okay, I don't like endothermic reactions. In combination to that, I'm decreasing the entropy. So Mother Nature's going, oh, this is such a bad combination, right? So I got two things that are working against it. It's an endothermic reaction, which Mother Nature doesn't like, and I'm cleaning the room. Mother Nature's going, no, seriously, this is just not in my wheelhouse. This is not who I am. So conceptually, Mother Nature is not going to like this. Mathematically, Mother Nature is not going to like it either. Because I've got 5 minus 2 times the negative 4. So I've got 5, in effect, this becomes negative 8. So I've got 5 plus 8, which is going to give me positive 13. So here's the point, is that no matter what I do here, even if I drop this to 0, okay, we'll go to 0 Kelvin, absolute 0. If I go to 0, I've got 5 minus 0, I'm still going to end up with a positive delta G, which means it's still going to be non-spontaneous. So in this situation, no matter what I do, I cannot get a negative delta G. So if you have a positive delta H and a negative delta S, this is a situation where it is never spontaneous. Okay? Ever, ever, ever. It cannot work. Now, let's talk about a negative delta H and a negative delta S. So let's go delta G. So I've got a negative delta H, so let's say that that's, I don't know, negative 10. Minus, and I'm going to leave the temperature out of it for now. And then I've got a delta S, which is going to be, let's say, negative 2. Okay? Now, so at this point, here's what I want to look at. This is going to be some temperature. We'll fill the temperature in just a second. So I got a negative 10 minus a negative, so I'm going to in effect end up adding this over here. So conceptually, Mother Nature is digging this because it's an exothermic reaction, because I've got a negative delta H. Mother Nature over here is kind of digging this concept because of the fact that if this temperature changes enough, I can make this work out where I can end up with a negative delta G. But the delta S by itself, Mother Nature isn't liking because of the fact that I'm decreasing the entropy. So Mother Nature likes this. So the enthalpy term, and here's your terminology, the enthalpy term is driving it towards spontaneity. The entropy term is driving it away from spontaneity because of the fact that the system is becoming more organized. Okay? So I'm giving off heat, but I'm cleaning and I'm getting stuff organized. And Mother Nature's going, I'm not digging this. So here's what you can do. You can solve for this temperature. So what you can do is set this side equal to 0. Because when the system's in equilibrium, and this is going to be an important thing that you also see, if you can set delta G equal to 0, the system can reach a point where it's in equilibrium. This is what's going to happen like a phase change when you go from a solid to a liquid or a liquid to a gas. That only happens when you can reach a point of equilibrium. So if I move, so what I've got is I've got 0 equals negative 10 minus T times negative 2. So I'm going to move this over here, right? So I'm going to have, in this case, moving this. So this is negative 10 plus 2t. So I'm going to have negative 2t equals negative 10. T equals 5. So if I'm at 5 degrees Kelvin, delta G is going to equal to 0, and this is going to be a spontaneous reaction. Excuse me, the system will be at equilibrium, because delta G is going to equal 0. So if I'm at 5, I'm at equilibrium. So this 5 is going to tell me, oh, this is the point where this system is at equilibrium. This is going to be where I'm going to go through a phase change, or it's going to go from like a solid to a liquid, or a liquid to a gas, okay? Or I'm going to cool it down from a gas into a liquid. So if you can find a temperature where delta G is going to equal to 0, that's going to be a phase change, and you can and this is going to be a critical temperature situation. So here's the deal. Now, if I make this 4 degrees, okay, so we're going to play the what if game. So if I come in here and I'm going to say, okay, I'm going to calculate delta G. Now I've got negative 10 minus 4 times a negative, was one step ahead, times a negative 2. So I've got negative 10 minus a negative 8. I get a negative value, which in this case is going to be negative 2. So that means this reaction is going to be spontaneous. So if I keep the temperature below that point, I'm going to end up with a negative delta G. Now, if I warm it up too much, the reaction doesn't become spontaneous. So if I go negative 10 minus, and let's say we warm this thing up to 6 degrees times negative 2, then I've got a negative 10 plus 12, and then I get a positive delta 2 as my Gibbs free energy, and the reaction becomes non-spontaneous. So if you have a negative delta H and a negative delta S, it can be spontaneous, but it has to be spontaneous below a certain point. So if you have negative values, it means it's spontaneous below a certain point. Now that doesn't mean it has to be really, really cold. It just has to be below a certain point, that's all. Okay, it just has to be below a certain point. So if you're looking at, like, for example, freezing water, if you're below 0 degrees Celsius, becomes spontaneous, because at 0 it's at equilibrium. If I go below that point, then it becomes a spontaneous reaction. So if you have a negative and a negative, it'll be spontaneous below a certain temperature, okay? So if you come up here on this sheet, I've got reactions dependent upon low temperatures. Delta H is negative, and delta S is negative, okay? So that's going to be that combination, a negative and a negative. I'm driving it towards spontaneity because I've got a negative delta H. It's an exothermic reaction. But my entropy term is driving it away from spontaneity because I'm decreasing the order in the system. Now, we have one combination left to go. So let's say that I've got a positive 10. So now I've got a positive delta H. So here's my delta H. So this is an endothermic reaction, which Mother Nature is going, ooh, not digging this. And then I'm going to go set this side equal to 0 because I'm going to find an equilibrium point, minus T. But then I'm going to have a positive 2 for my entropy term. So Mother Nature is going, okay, I'm cool with this, okay? I'm not liking this, so this is not driving it towards spontaneity because I got a positive 10. But I've got a positive delta S, which is driving it towards spontaneity. So I'm cooling it down, it's an endothermic reaction, but I'm making a mess, so at least I got this going for me. Now, when I have that combination of two negatives or two positives, I can solve for a temperature. So then I can go, okay, I'm going to move this over here, right? So I've got a negative 2, I move this over, I got 2T equals 10, so oddly enough, T equals 5. So if I put in a temperature of 5 degrees, I get delta G equals 0, that's a spontaneous reaction. Excuse me, the system's at equilibrium. I bet, the system's at equilibrium. If I put in exactly 5 degrees, so this would be a phase change. You're melting, you're boiling, something is going to be happening here. Now, let's bump this up to 6 degrees and then see what happens. So if I go to 6 degrees, then I got a positive 10 minus 6 times 12, which is 10 minus 12, which gets me a negative 2. Okay, so here's the cool thing on this. So if this temperature is above that critical point, then it becomes spontaneous because of the fact that now this entropy part over here, I'm subtracting a big enough value from my enthalpy term to make my delta G be a negative value. Okay? So if I take 10 minus 2, or 10 minus 12, I get a negative 2. Okay? I get a negative delta G. I get a spontaneous reaction. Now, let's say that we're below that point. Let's say that we have 10 minus 4 times 2. I get 10 minus 8. I get a positive 2. Guess what? Now I've got a positive delta G, and it becomes a non-spontaneous reaction. So this is like, for example, this is why water won't boil below 100 degrees Celsius. Because if you're going to boil water, number one, it's an endothermic reaction because you're dumping energy into it. But you're increasing the entropy because you're going from a liquid into a water, a liquid into a vapor phase. So boiling water is temperature dependent at 100 degrees. So you're increasing your entropy by boiling water because you're changing it from a gas or from a liquid into a gas. It's an endothermic reaction because you have to dump energy into it. This is why we put it on a hot plate. Okay? So if I'm below a certain temperature, it's not spontaneous. But if I'm above a certain temperature, it becomes spontaneous, and then I can reach a point of equilibrium. So if I've got a positive delta H and a positive delta S, that means it can become spontaneous above a certain temperature. So this is how I always remember this. Okay, I don't care how you remember it, this is just an option. If people that are positive, okay, they tend to lift you up, okay? Wow, okay, great, you know, hey, I'm around, you know, I'm around Anna and, I don't know, Bruce, okay? And I'm just picking out names, don't take this. I'm around Anna and Bruce, they're kind of bopping around going, oh, great, you know, we're having a good time, okay? Hey, that's going to lift up my spirits. So if you have a positive and a positive, that means it has to be above a certain temperature. Now, don't think this has to happen at a high temperature. It just has to be above a certain point, okay? Don't think, oh, this will only happen if you're like at 1,000 degrees and you're on the surface of the sun. No, it just has to be above a certain temperature. Just like this one just has to be below a certain temperature. That temperature might be 500 degrees, okay? If you're below 500, that means that reaction is going to be spontaneous. So don't flip out when you see high and low temperatures. It's just relative to a point where you can reach a point of equilibrium. So if you are dependent upon high temperatures, you have delta H is positive and delta S is positive. So here's the 4 things that you need to begin to think through. If you've got 2 positive values, enthalpy and entropy, that's temperature dependent on high values. If you have 2 negative values, it's temperature dependent upon low. If you have a negative delta H and a positive delta S, that reaction is always spontaneous because